In the task allocation domain, therefore, a very important question is to find out a mechanism which satisfies all these three properties. We have discussed two properties, serial dictatorship and proportional mechanisms, which are plausible mechanisms in some way, but they do not satisfy all these three properties together. So turns out that there exists a very interesting mechanism called the uniform rule, which was proposed by Sprumo in 1991, which satisfies all these properties. Let us look at what this mechanism is. So let us look at this picture. Suppose there are 5 players, 1, 2, 3, 4, 5, and you have this total amount of task, which is denoted by 1, and the 0th amount of task, no task. Now just for the illustration, for this example, assume that the sum of these peaks is less than 1. So there is not sufficient amount of the player's favorite things do not add up to 1. We'll have to overload all these players. Now the way this uniform rule works is as if you imagine you initially fill everybody's task allocation with 1. So it is way more than 1. It will be actually starting with n, but that's the starting point. Now you reduce this level at an uniform rate for all the players, right? Now whenever you hit some player's peak, so let's say in this case you have hit this third player's peak for the first time, you allocate that peak for player 3 and keep on reducing that level further, also keeping a count on how much allocation we have already done. So for all the other players we are at this level. So this sum, if this sum is this sum along with the share that we have assigned for player 3, if that is equal to 1, then we'll stop. If not, we'll continue moving this thread. So you can think of this as a thread which started with one allocation of 1 unit of task for all the players, and then you are uniformly dropping this thread until you have the situation where the sum of these FIs are actually equal to 1. So maybe in this context, let's assume that player 1 and player 3, these two players tasks are assigned to their favorite positions, that is their PIs, but for others their peaks were not reached, so everybody else will have something like this share. So for all the other players the share would be the same. So that is the uniform rule. The name comes from the fact that we are uniformly reducing it, and whenever someone's peak is reached, they are given that share, their peak share, and for the others we are going to reduce it until their peak is reached, or sum of Fi is equal to 1, whichever is earlier. So this is really a nice mechanism. We'll see that what are the properties that it satisfies. So you can also think of a very similar mechanism when you have the condition when sum of Pi is actually greater than 1. So in that case the thread starts from the bottom. So you allocate everybody a 0 amount of task allocation, and then keep on increasing that thread, bring that thread upwards until you hit some ones. So in this case, suppose 5 is hit for the first time, and then 2 is hit, and then at whichever point the sum of this Fi becomes equal to 1, at that point we should stop. That is the uniform rule. So how can we put that observation a little more formally in mathematical terms? So suppose the case 1 where the peaks are sum up to 1. In that case, everybody is given their peaks, so there is nothing to worry about. Whether you draw the thread from upwards or downwards does not matter. It will end when everybody is given their peaks, because that is equal to 1. So until then it will continue. Let us look at this non-trivial cases. where the sum of this pi is less than 1, then we can see that this is going to be a max of their own peak and some mu, where mu p is going to be found from by solving this equation, that you have this this max over pi comma mu, and when you are taking this sum, it should be equal to 1. So either what can happen is the mu is larger or the pi is larger. If pi is larger, so that means that the example that we have discussed, we are starting the thread from upwards. If pi is larger than mu, so finally we saw that in that case mu has actually settled at this point. So if mu is larger, then we'll pick mu for that player, which happened for player 2, 4 and 5. But if pi is larger, then we'll pick pi. So that is exactly what is happening here. So we are either allocating that pi amount of work or mu of p amount of work to that player. And similarly for the other case where the sum of this pi is actually more than 1, then we are actually starting from bottom. So we are picking whichever is smaller among pi and something lambda of pi, and lambda is essentially solving this. So in the same example, for 5 and 2, let's say their peaks were smaller than the lambda value, which was somewhere a little above that. For all the other players, lambda is actually smaller than their peaks, so therefore you are going to pick lambda. Now the most important questions. So is it anonymous, Pareto efficient and strategy proof? And turns out it is. So this is a result by Spruma, which shows that all these properties are satisfied by this uniform rule. So we can almost immediately see the anonymity. This is quite obvious. All that matters is this peaks, and whenever you alter or permute these peaks, so whoever has that particular peak, he gets assigned the same amount of job. So it's completely anonymous. So to argue about the Pareto efficiency, we can argue it in a very similar way that we did in the context of proportional allocation. So this thread will always, for this case where sum of the pi is less than 1, will stop at their pi or at least as much as their pi. So it will stop above their peak, or maybe it will stop at the peak itself. Now what does that mean? So maybe it is easier to explain from the figure itself. So if you look at this mu, which is giving this amount of task for players 2, 4 and 5, and for player 1 and 3 it is giving their favorite peak. So there is no way we can improve the allocation of players 1 and 3. They are already getting their most favorite one. If we try to improve any of the other players, let's say we are trying to improve player 2's allocation, the only way we can do it is by giving them an allocation which is closer to their peak. That is, we are going to reduce their allocation. But in order to do that, we'll have to increase some other players, so either 4 or 5's allocation to be more than that, because at the end of the allocation we'll have to keep this equality satisfied. The sum of all these allocations should be equal to 1. So if you reduce for someone, you'll have to increase for someone, and because of the single peakness, that will be preferred less by that individual. In this case, player 4 will like that allocation to be worse. So therefore this particular allocation, the current allocation itself, is Pareto efficient. There does not exist any other allocation which can make everybody weakly better off and at least one person strictly better off. That's not possible. Now let us come to the strategy proofness context. So for the case where the sum of the peaks is equal to 1, this is quite simple. Every agent gets their peak. There is no reason for anybody to deviate. Now let us consider the case where sum of this pi is less than 1, and we have already seen that the uniform rule in that case will give at least their peaks. It can be more than that, but it is lower bounded by their peaks. Now, for the players who have already got their peaks, there is nothing to manipulate. They have already got their favorite allocation. So the misreporting can only happen from the point of view of the players for which that thread actually stopped before reaching their peak, right? So which means that this mu p, the current position, the final position of the thread is actually more than their peak. Now, how can player I change the allocation? Again, going back to this. So let's say player 2 is trying to improve its allocation. The only way it can change is by reporting its peak to be something above than that. That's the only way it can change. In that case, it will be allocated that particular peak, because the thread will stop. It's going beyond that point. So if it is allocating that amount of that share of the task to player 2, that is going to be less preferred, because player 2 has a single peak preference at this point. Anything more, any share which is more than that or less than that is equally worse for this player. So it will not like to misreport to change the allocation in any way, and that applies to all the other players who have not been granted their most favorite share of the job. That is quite interesting. This mechanism is actually strategy proof, and you can use the same argument when you are drawing the thread from downwards. That is for the other case where sum of the pi is greater than 1. There also you can see that this particular agent, whoever has not reached, so for instance in here, the only way, because the thread stopped somewhere below, the only way it can change it is by reporting some peak which is below that, but they strictly prefer that less than the current allocation. So that will also not be beneficial for them. So it is strategy proof in all these three cases. This very elegant mechanism of uniform rule actually solves this problem in the context of task allocation. It satisfies these three properties: anonymity, strategy proofness, and Pareto efficiency. And I will just state and leave at that point. And this converse of this result is also true. Will not prove it. And this is the classic result by Sprumo, which shows that even if you try to design any other mechanism, you can't. If you are restricting yourself to this task allocation domain, then if you are looking at this property strategy proofness, Pareto efficiency, and anonymity, then uniform rule is the only rule that satisfies these three properties. So the statement says that a strategy proof, a social choice function is strategy proof, Pareto efficient, and anonymous if and only if it's a uniform rule. As a reference, I will leave you with this paper by Sprumo, which is titled Division Problem with Single Peak Preferences. That has the full discussion of this rule and also the proofs.